For similar triangles, the ratios of the sides of the two different triangles are equal. For example, the ratio of B over C is equal to the ratio of B1 over C1. Here's B, here's C. This would be the opposite side to the angle theta over the hypotenuse. And here is the opposite side again, but of a similar triangle to ABC. This is A1, B1, C1. B1 divided by C1 would be the same ratio as B divided by C. That is what these trigonomic identities are going to be based off of. Now, since B divided by C is equal to a constant, for some angle, it doesn't matter what size triangle I have. I could continue extending this triangle outwards, this way and this way, and the ratio of B to C, well, I should probably pick a different constant. I'll call this constant Z. So if I continue extending this triangle, the ratio of B to C is always going to be equal to this constant. So that's what I'm going to take advantage of. If I know what this constant is, and I know one of the sides, then I can figure out the length of the other side. So suppose I have figured out a numerical value for Z. If I wanted to know B, and I already had C, then I would multiply C to both sides, and I would have the value for B. So that is one of the useful parts about these identities. Now, the reason that these are not equal to, I don't know how to say it, the reason they don't have a single value is because the ratio is going to be dependent on the angle theta. Because if this triangle were shorter, suppose this angle was smaller, then the ratio of B over to C would be different. B over to C is some value right now, but if this angle was smaller, then B would shrink a lot. So if I had a tiny angle, just like here, B would be very small in comparison with C. C would have changed slightly, but not as much as B. So the ratio would be different. So what this means is that the constant is dependent on the angle theta. Each individual angle has its own specific constant that it's going to be equal to. Now, no matter what that constant is, B over C is going to be equal to it, but the constant is dependent on the angle. And that's why this notation was invented, sine of theta. Basically, what it's saying is that B over C has its own ratio, and it is dependent on the angle theta. So sine is the ratio of B over C. Cosine is the ratio of A over C. So the adjacent side over the hypotenuse. And tangent is B over A, the opposite over the adjacent. And then cosecant, secant, and cotangent are the inverse, or the reciprocals of those values. And cosecant, secant, and cotangent aren't really that important today. The reason they were important a long time ago is because, like I said, each one of these angles has its own specific constant, and what mathematicians did was they just calculated them. And they used to have these big tables that have sine, and then 1 degree, 2 degrees, 3 degrees, all the way down to right to 90 degrees, really. Because if this is a right triangle, these two angles must be equal to 90 degrees of the sum. Now this one could be 89 degrees and this one could be 1 degree, or they could be 50-30, or anything along the way. Or 50-40, I mean. That's pretty bad. So what they did was had these huge tables. Now with modern calculators, since cosecant is just the opposite, or the reciprocal of sine, I can just quickly put the reciprocal into my calculator and I get that, but they did not have that luxury back then. So these were invented. They seem kind of pointless nowadays, and they are pretty much kind of pointless. The only reason they had it back then is because they didn't have calculators and were not able to quickly calculate that, so they just had a table of that as well. So these ones aren't really that important. I never really think of them. I haven't really found much use for them at all in my entire life doing math, and I've done a lot of math. And the only thing I can think of that was vaguely useful about them was that they kind of made some integrations a little bit easier. But honestly, I could think of those in sines and cosines and tangents. It doesn't really matter. It's the same thing. But however, sometimes it's just written easier. That was the only use I found for them, really. I'm sure someone will argue against me, but that's just from my personal experience. So that's basically what these trigonomic functions are. It's basically a way of dictating what constant. So if I have some value b over c, its constant is going to be dependent on the angle. And that's what that function means. The function just finds. It's just a representation of some constant. And ordinarily, I'd have to look, or at least in the past, I would have had to look it up in a massive table. But now with my calculator, it already knows what they all are. So I don't have to do that. So that's what the trigonomic functions mean. That's where they come from. That's what they're for. It's basically a stand-in for a constant of a particular angle. And these constants again come from the right triangle. And they are based on the ratios of the different sides.